I'm now gonna show you an introduction to Grasshopper, which is the graphical algorithm editor of Rhinoceros. In Rhino 6, it's actually integrated into the program, so if you click this icon here, it will start. If you're using previous versions, you have to write Grasshopper in the command line up here to start it. So the concept really is to make everything changeable throughout the design process. So here I have constructed a grid already based on these squares here. It's made with array, rectangular array here, for example. You can also move these. But what if I want to change rounded corners on all of them at the same time? Here I would have to go into fillet and simply change all the corners in each and every square, of course. Or I would probably simply rearrange this one, redesign it, and then rearrange based on this first square here and spread that all along. But wouldn't it be interesting if we could change all of these or selected parts of these in one go? And that is what Grasshopper can do. So it's more or less a recording of all the things you've done. If you see here, it's like my last history of commands which I've done. So you could say that Grasshopper builds the whole structure up, the whole history of commands and operations, including selecting specific points or curves to build surfaces. You can always go back to see how that works and to see how that was built and to re-edit that back in time, so to say. It sounds pretty abstract, so let's open Grasshopper and see how that looks like. So when you open it first, this window is probably maybe taking the whole screen, or I have now set the screen so that it's half, like this. You can also double click to just toggle its visibility. And then you have, I can probably set it like something like that so it looks good on this screen as well. So when you open it, you see it's different depending on what you've done before. So here's my last files that I've used. And then one simply takes out components from up here and puts them in. And they look something like this, only like examples right now. So cables go in between these. So I can have a cable from this one going into this component, and it continues to somewhere else. And what is this? Like a really small, it's actually empty things that I've done now because it's orange. But just to give you a first idea, we have a point. It builds, maybe you have several points here. We have 3 points that build a surface, and that surface gets moved to somewhere. You see, so that's already using 3 points that I've drawn, maybe in Rhino or in Grasshopper. I explain the difference afterwards. A surface is built and it's moved. So we have 3 sets of operations already, even though these are empty. So this is just to give you an idea. So I can always change the points, right? I can always do this and the surface will change. And I can also put something else into the move component here to tell it to go somewhere else, right? That means that this is a little bit of a history visualized, because first it shows the points to make a surface, and then you move them, so you more or less visually see a graphic representation of the design process. Even though it's very small in this case, you can always go back and go forwards and add something and change it as you go along. So if we for example, would build this grid as a first test. You don't. I urge you to try to follow me when I'm doing the things on the screen. But I also show where I'm getting at. So I show the goal already now to make to show the difference. So you remember I had this grid in Rhino, just as an example. I can also do a grid here, and I will explain this a little bit more closely afterwards. The grid is positioned always in the center here, and I have actually cells coming out of the component. I can extract the center points of each and every cell. A plane is also visualized here, and I can, for example, do scale on all of these in a specific amount. So if I hide these, you see more or less how it works. I can change them all in one go. So to answer the question about the problem we had before when I drew in Rhino, could I edit all of these at one go? Yes, I can, because I can then find the same command here, fillet. So I can fillet the radiuses, making round corners on all of these in one go with a slider like this. And if I hide the previous one, see that actually is happening now, which means I can multiply objects and then edit them all at once, or a selection of them, a portion of them. I can actually select, let's say, only the ones, the 9 ones in the middle here, or the 3 ones in the corner, depending on different components, Grasshopper components that I add to this algorithm. So this is an algorithm now. So that went pretty fast, but I just have to show you some small setup to make you understand what this is all about. So we have a little design history already. First we made a grid, right? We extracted the area to scale something, to scale the cells that we generated. And the center point is the center of scaling. The scaling takes place here, is a factor. Then we have the same grids actually translated into here. So it's more or less the same list going in. And then that list of objects goes into another one. So it gets more or less copied, you can say that, into a new component, which adds another layer of design operations onto the object. So there is actually no copy in this system. There is actually only a transition into a new state, a new shape. So you're editing the shape as you go along. So, and you see that this is only the last one is visible now. That's because that's the latest thing I did, right? So if I hide that, take out the preview, I don't see anything. So I can repeat it from the very beginning. We had the grid. That's like the foundation of this setup now. And then I want to scale it, so I need to extract the center points, which I did with this component. And then I scaled it, right? I hid that now too, but I preview the scaling, and you see everything you select in Grasshopper turns green, also in Grasshopper and in Rhinoceros. So if I pull that back and forth, that's a scaling. So everything else is still visible, right? And finally, I added a fillet curves, which makes the corner rounded. Certainly, at any point, and this is the advantage. Of course, you see already I can always change this, but I can also swap between these. If I don't like it, I can just test what is this like. Now I jumped and used this, the initial cells, the squares, to make those corners round instead. So I just swapped the cable to this one, right? And I can go back and forth like this. So this is the main idea of Grasshopper, and then you can make very much complex things that you can see in my other videos. I will put the link in here. So here is the address for my Vimeo album with my Grasshopper videos. So vimeo.com/album/5608375. I will also put that in the description of this video, so you can link there immediately. So now I showed you a little bit of an introduction to what you might expect from this program. Also, of course, we can change the size of the grids so that everything moves along accordingly. You see that sometimes one wonders what happens with the beginning here, yeah, because there is actually default settings already here. The position is default settings, the number of cells, and in each direction is also default. It's always 5 inside of this component. But I will try to build this again in the end of this video. And before I do that, I want to go through all of these curtains that you see up here. There are quite many of them. And I will show you how to browse through them. So I can actually delete this. I will have my Vimeo link still visible. The thing with Grasshopper here is that it's actually quite compatible with Rhinoceros. So if you already know commands in Rhinoceros, you will be able to find them in Grasshopper. So either you double click and search for a component that you want to use, for example, a point. The whole selection of point that, components that has something to do with a point comes up. There are quite many more than these, as a matter of fact, but these are they are sorted according to their names, of course. Otherwise, points, of course, builds both curves and surfaces. If you do the same thing in Rhino, tap area there, sorry. Point, the same structure comes up, it just drops down like this. So if you're familiar to Rhino, you know that if you just simply choose point, they want to know where it is, right? So this is the same thing more or less in Grasshopper. So you have a command line, you put in a specific operation, and the program asks you something, right? This is the inputs that I showed you here before. So if I take, if I search for point again, point, and take, I'll take an XYZ point for this example, XYZ point, the construct point it's called actually. So I have a point already, and you can see that there is a point here in Rhino space as well, in Rhino workspace. The thing is that it has default answers, right? It says 0, 0, 0. So it's already answered the question of the location of point object, which Rhino did. Rhino asked for that, right? If I take in point again, hit enter, location of point object, I can put it maybe on 10, 10, 0. It lands there. You see the difference there? I didn't put 0, and here is already 0 in it. So if I now go in and say 10 here as an answer to this component, you can consider all components in Grasshopper a selected operation in Rhino, and Rhino asks you questions, and in Grasshopper functions similarly. It's only that the questions asked are the input already. So if I put in 10 and 10, it lands in the same spot. So that's more or less the exact operation which I just did in Rhino. I hope that is understandable. So I can delete the point there. Yeah. So now that the point is on 10, 10, 10. I can pull back. It's only on X. I can pull back again and put it on Y, in the Y direction in 10. and it lands there. But how do I know that if I open a component like this? By the way, if you open components, just try out a little bit. That's a very handy command, a shortcut. If you press Control, Alt, and left mouse button, Control, Alt, left mouse button, you can actually find out where they are, all the positions of the components in the structure, the tool palettes, let's say. So every time I open something, I have to want to stress and emphasize, even though if I search for something, I hover and then the info comes out and actually tells me what it's going to do. So if I hover over construct point here, for example, it says construct a point from X, Y, Z coordinates. That sounds good, so I will choose that. Then I just click on it and it comes out, right? I have a new one here. But then I want to emphasize that we hover on everything. So we hover even when we take it out into the workspace, we hover on the title. So that there is this construct point, parentheses PT, that's the abbreviation for this command. Construct a point from X, Y, Z coordinates. That's exactly the same text as we found when we were hovering, right? But it's always good to read it again, because there can be additional info when you do this. And this is how you learn how to use the components in Grasshopper. Because inside here, there's a little script that that the developers have written that tells a point to go in a specific position, right? So, and after you hovered the title, I want you to hover the output so you know what it's actually giving you. And it's giving you, if you hover here, it says point. It says it creates a point coordinate, and it's also giving a little bit extra info additionally. So point coordinate, one locally defined value. That's a standard kind of phrase that Grasshopper uses. And in underneath it says the 0.0,0,0. So that's actually what has been produced. And if you look in Rhino workspace, that seems to be very correct, doesn't it? But where does that come from? That's the question, because the question about position has already been answered, right? That's why you now should hover all inputs. So X coordinate, there it says 0. On Y coordinate, it says 0 as well, and on Z coordinate, it also says 0. So this means you can put your own inputs here. So the easiest thing to do is to use sliders. You saw before that you can also take out this this panel, double click it and type something, and never type enter afterwards, by the way, because if you do this, it's going to break the command, the code line. It's not going to work out. So you could do this and write whatever you want and put it in, and the point will move. But I strongly recommend to use sliders, which are on parameters and sliders. Take that out, and you see you can pull back and forth on this slider. If you insert that into the X input, you see how it moves. It moves quite little, you know, but that's because you have to go in and edit it by right-clicking. And then you can double-click in, for example, max here, and put in 10, like I did before. And also in the slider you have floating point numbers. That means the decimals, how many decimals you want to have. You can also have 0 decimals, of course. But that 0 decimal is more this on the end, the integer numbers, they don't have any decimals. Then you also have even numbers only. Can try to pull here, you see 0, 2, 4, 6, 8 and so forth, and you have odd numbers. I usually, to be as exact as possible, is of course good to use floating numbers, but it depends on what you design. So I press OK, and then I have transformed my slider from 0 to 11. Like that, I can change it again. So from 0 to 10, 0 to 10, and then I can, if I want to have it in the Y input, I do that too. But if I want to release this now, I press Control and pull back. So Control and pull back, and I can also add, if it's like you can add the same, you can add many sliders in the same input actually by holding Shift. But to copy, I want to have a copy of this. I don't have to create a new one, so I can simply select it and press Control Copy, Control C, Control V, and then it pops out. And now, mind you, the name is actually changed. This is a new feature. Well, it's not such a new feature, but in the latest years, it has become so that the name slider, which says here, gets changed depending on where you put it in. So now it's called Y coordinate, which is quite good actually, because you see where you are. So if you have it like this now, you can go up and down again in this manner. And of course, you can watch it also in 3D. If I go to my perspective view by double-clicking on the viewport title, and I can also apply this to the set coordinates. So that's a basic setup, one example of a basic setup in Grasshopper. If you want to read more about the program, there is grasshopper3d.com, where you can find tutorials, explanations, discussions, and so forth. This is actually, though, beginning to be dismantled more and more. There used to be a forum here as well, but the main forum for all questions and such things, they are at discourse.mcneil.com. Here you can find, here is actually a collection of all the systems they offer from McNeil. So there is Rhino, there is Serengeti, and there is Grasshopper, of course. Different discussion groups, and it's a very, very good forum. It's amazing how fast they answer and how much info you can find here, actually. So you should keep that in mind. Discourse.mcneil.com. So we will continue. I can let this be here actually somewhere. You see, you can simply, just like in Rhino, you simply make a window over everything, and you can move them around. You can move it around like that. You can even give this a group, like pressing Control G, and you can even right click and type something first, setup, and then I can pull the purple part here and pull it away. So this is the first thing we looked at, so to say. But what do we have here now? You see, I'm pulling back and forth. So just like in front view and top view in Rhino, if you right click, you pan. And if you scroll, you zoom in and out, because there can be quite many components. So you have to zoom out like this to see the whole thing you did. So it's good to have this navigation. And also, of course, you can find components by pressing Control Alt left mouse click. Because often it is so, you have found something and then maybe you realize, I want to add something similar to it, and then you will find in the curtains something similar to it or related to that component. And you can open all these by pressing this black title underneath, and it will pop up. But what do we have here really? First we have parameters. That is, those are the most basic components that we have. And in parameters and geometry, if I click the black title here, everything comes out, so you only see a selection up here. You can read the titles already here. Point, we saw that in the list when I searched before. Circle, curve, plane, rectangle. And if you hover, if you pause a little bit and hover, you see that contains a collection of rectangles, it says. Here we go to curve, contains a collection of generic curves. So these are actually empty components, all of them. If I take, for example, point here, it is orange. So everything that is orange is empty already. Now I selected it, of course, and it gets a kind of a yellow greenish color, which also means it's empty. These are white, so which means they are actually functioning and they are filled with something. If I hide it, it turns dark gray. We'll come back to that soon. So, but this doesn't contain anything, and it's actually what we see here is, of course, this point, right? This means that all the components in Grasshopper that have a black hexagonal background, they are communicating with Rhinoceros or with something that you built in here. So, for example, I can draw a point in Rhinoceros, and now I can pick that point into Grasshopper and use it for something. So, for example, I do that now. I right-click and I go to set one point, and then my Grasshopper window is going to disappear in this fashion. And now I have more space to select what I want. I could also have chosen to select multiple points, actually. But now I'll select this one, and immediately Grasshopper window pops back, and the component turns white, which means it actually contains something. If you selected the point you drew that I drew in Rhinoceros is turning green. So now that's communicating between each other, which is quite an advantage, because you can then you have the interaction between your mouse in your model. Maybe you import your model from somewhere else and want to cover it with some pattern or something. Then you can every time you transform a curve here or move a point or whatever, it's going to get communicated into Rhinoceros, into Grasshopper. Sorry. The same thing goes for example, a curve. I drew a curve here, and I open the curve component, which is also empty. I'm going to right-click, set one curve, and then that's actually communicated in. Yeah, so you can imagine that you can also then build surfaces from between these curves. So we'll show that later. So here in the first is all kinds of things like that. Depends on what geometry you're working with in Rhinoceros or in here. So in here, for example, if I don't want to have that, I can take another point. Maybe that is not what I wanted to insert into the point. I can use this point and simply transfer it once more. Now I have it 2 times, it's the same point. But you can imagine if you have maybe 100 points in this one, you can also, or in different components, I mean, not only in this one, maybe you have 2 of these. Like that, I copy the whole thing. And then there's another point, and I can simply, by holding Shift, by the way, mind you, we can insert several cables into one component. So now this component contains these 2. And yeah, well, as you go along, you will notice why that would be an advantage at all. I mean, from here you can build a surface or something like that. Maybe it's and then you can simply channel in multiple points into that surface or curve that you want to build in Grasshopper. Yes, so that was a little test there. We go on here, primitives. These are numbers and integers and texts, also empty data paths and stuff like this that you can extract from other components. Then we have all kinds of inputs. We already looked at the number slider, right? But you also have the control knob, which is here, but I can also pull it from there. It's a different sort of input, more or less. If you really want to have this, it's a kind of a fun feature, I suppose. I usually only use the slider. We also have graph mappers. We can channel series of numbers, mass of numbers into a graph, and we can, for example, I'll take a sinus graph here, sine graph, and then I can manipulate all the numbers going in. So this could, I could theoretically, let's say, manipulate the diameters of numerous spheres by doing this. So then there would be a small radius and a high radius, and a small radius and a large radius here. Yes. And we also can add colors and things onto the geometries we make. We also have a panel here. This is very handy, actually. Either you can type something in it, but you can also watch what's going on inside the components. Like this, you get more info. It's more or less exactly the same thing as hovering the output, but now you can see it the whole time, which is very handy when it gets more and more complex. We also have utilities here, which is more or less a sort of you can watch the parameters. You can pick a single item from a data tree. You can edit clusters and so forth. So if we continue to the next section, mathematics, we have domains, which sets the lowest and the highest number in a series of numbers. So this is now we're just making an overview, right? To see a little bit and open these to see what's going on. A matrix deconstructs a matrix into component parts. It's more or less a series of numbers or series of of parameters that you can change. Operators, here we can add numbers to each other. Addition, completely normal, like 1 plus 1. You can also, as we go along, simply open these and see what they look like. So, for example, we put 1 in here and 1 in the A input and the number 1 in the B input, and it will result in 2. So it's pretty understandable. And we have the same thing with multiplication, division, subtraction. And here you can swap the numbers. You can change them so they turn negative, for example. Compute the negative of a value. That's, for example, a slider. So if I put this in here and I hover, you see it's minus 6.1558. So you simply invert the number into its negative. I can jump a little bit here. Mass addition. If you have numerous numbers, you can add them to each other instead of 2 inputs. This is a mass addition, looking like this. So then you just put all the numbers into the slider here, and the result will come out. It's very useful for combining lists, and we're going to get into lists as well because it's very crucial to this. So, Grasshopper is based on parameters. And it's based on lists and coordinates. And all this list is descriptions of what's going on in the components themselves. If, for example, I add this panel, this is a list. So this is the 0th list of what's going on in here. So it could have been more. So this is a very simple list. If I have, for example, let's say I have 3 points there, and I take those into this point instead. Select multiple points. And then I look at that list. It's one list containing 3 points. So this is how the program is structured. Then we can have also nested lists. So that 3 lists containing each 1 point looks like this, and then the cable changes. And this is something that we're going to look into more and more as we go along, also in the other videos that I made. Then I explain that more closely. So if I go back to where I were, why am I saying that? It's because to select from those lists, we can use, for example, we can test the list according to numbers. For example, the x position less or equal to the number 1, then I can select these by using equality, for example, or larger than. So all the positions in x direction larger than 1 will get a true. So then we can affect the list by true and false lists. So everything that is true will be shown, everything which is false would be not visible or actually disabled from the system, from the algorithm. So now you know where they are. So then as we'll go along, and as I said before in my other videos, you will see more concrete examples from this. If we move along here, we have similar things, more complex, as in this list. Here you can calculate things, you can take the square root of a number, for example, cube root, you see. And then we also go one step further. You can actually make equations. So the first one is the most useful one, I think. We can look at that. You can put an equation in here using x and y. So everything you put in x and y will be affected by this expression that you have put in, looking like this. For example, you can write whatever x is times y square, for example. And then it turns red, and you can put a slider into each of the x and y, and then the equation is actually working, you see. And then you can hover and see the outcome of it. Whoops. Not like that, of course. And there you have if I hover again, I see my equation that I just wrote, and the result of it, depending on what's coming into x and y. To complex that even more further, we have something like this, but it's actually not so complex. It's actually the same thing, but the difference is that you will actually see your equation being written here at all times. So it's a matter of taste which one you prefer from those two. Then you can also go into much more complex things like C# scripts, like Python and Visual Basic scripts, depending on what you want to do. These are very useful sometimes, actually, but it's more for complex operations. Oh yeah, here you can actually use time and date if you want to. Depends on what you're simulating. You know, if you want to use, for example, the movement of the sun or something like this. We also have preset sine values and cosine values and tangents. For example, if you want to construct a spiral or something like this. Trigonometry is also there. So all the mathematics setups you can find in the math section. We can go one step further and see sets. Here we come into lists again. So list item, you pick a specific index in the list. You can measure how many objects are in the list. So more or less when I say list, I mean the components. So that's what you're measuring. So anything you draw in here is going to turn into series of points. It's not only one point in here. It could be one. It can also be 1 million points if you want to, and that's why it's called. That's why the software is referring to lists again. For example, if I take in list item here, the value on default here is 0. So what you saw already when I showed this list, I can show it again. 0, 1, and 2, right? So they always become their own names. They get names automatically, always starting with 0. So if I would have 1,000 points in here, it would be a list from 0 to 999, if that makes sense. Now it's 3 points, so now it's a list with names from 0 to 2. So what happens if I insert this into a list item? It's simply a filter between these points and something else that I want to use again here. So 0 was the, here you put in what name you want to pick out, which one of these. Their names are indexes, exactly like here, like 0. So if I select it, one of the points, not only one of the points, but the point with the index 0 will be selected. So also here I can put a slider and maybe make 2 as the most one, and integer. Now I have from 0 to 2, right? And now I can toggle between these. If I keep this selected and then I pull on the slider, I see that it selects only one of the points. So this is a filter. Here is 3 points, and I put a filter in between to select only one of them. And toggle between them like that. We can also make the opposite. If we go to sequence, we can take out that index, cull index. So this is list index, means you select it. Here you mean you cull it, you remove it from the list. You can also see that when you hover there, cull index, cull or remove indexed elements from the list. I'll take that in, and the opposite is going to happen. So you see now there are only 2. No, there are 2 visible actually. Here's 1. So this is the exact opposite. And these 2 components is something that we will use very often. It's very common and very handy to use. So you see here when the removed item is selected, cull, it's called cull index. Then I can swap, and it's only 2 visible. Further on, set differences. We have create set. We can create a different of 2 sets collections. Create a symmetric difference of 2 sets. This is also quite hard to visualize right now, that we have to put into a real situation to know what it is. But in general, you can say that on sets, you simply rearrange lists. You can nest them and flatten them into different. If you have a nested list, you can make it into one list. You can make more complex lists, like nested trees, I mean, many branches. And of course, if it's in complete disorder, the list, you can also go into the first one here and see sort list, for example. That's also a very good command for making things in order. If we go further, we go to vector, and we can see that we field. We can, in this case, we can create magnetic coordinate fields, for example. But more interestingly for us right now, in the beginning as well, is to make grids. You can make a hexagonal grid, radial, rectangular grid. I already showed you square grid. So hexagonal grid, if you open that and just test, you see that grids like these are being built, and then you can of course transform them afterwards. For example, with rounded corners, like I showed you before in the beginning. You can create a radial grid. So I urge you to take these out and check them out and hover all the inputs. Maybe put slider in there to see what happens. We also have a triangular grid that looks like that. You see now they're all on top of each other, of course. But if you right click and set another plane, then you can actually rearrange them a little bit so that they're not on top of each other the whole time. Set one plane. You simply have to give X and Y again to put a little bit too much far away from the other ones, but you see that's the radial grids, and all of these are cells, so there are closed polygons, all of these, so that's very handy, of course, when you build things. So also all of these are closed polygons, the hexagons and the triangles as well. So you can always pause this video and go in and open these grids and test them out. Hover, put in sliders and transform them accordingly to what I did in the beginning of the video, then you will see how they work. So, but I already showed you the plane, right? I clicked and I set one plane to position it. And all these planes, they are positioned here as well. So you can actually, you can imagine you can make numerous planes in different positions. So XY plane, as we've noticed perhaps when you tested this, are the, if you hover on the P input on the hex grid, for example, world XY it says. So all components has a position. If it's a geometry, usually the position input is the top one. And here on default, world XY simply means that it's in origo, so it's in 0, 0, 0. And then you can construct your own planes. So if we theoretically now say that you will generate thousands of planes and give them different directions in X and Y and Z, they can more or less float freely in a 3D space, in Euclidean space here, and then you can put them into the inputs. That means that you can make numerous hexagon grids as well, or numerous curves, or whatever it is. So these are placeholders for different geometries. And if you hover these, you can see that plane offset, you can offset the plane, you can change the normal of a plane, you can build your own plane based on three points, for example. You can also draw directly in front view, for example, or in right view. So these are actually, if you use this, and I'll take that out, anything you draw on this will be drawn in front view. This is an XZ plane, so if I add that instead, the whole pattern, the hexagon grid that I made, the tessellation here, is going to be situated accordingly. So that's quite interesting. So I urge you to experiment a little bit with that. Here's an YZ plane, for example, for the triangular grid. Let's see how that looks like. It pops up there, right? So one has to get a little bit familiar with this. And then, of course, adjust the other inputs. If we go on more further here in the vector section, you see you can here is the menu with points. So construct point. We already did that, right? It's here. So that's the same component. You can deconstruct a point as well. What is that? You can always take it out and try. That means you actually extract all the values that we already have in the sliders. So if you hover, you see it's the same number coming out. So you can deconstruct the coordinate here into its X, Y, and Z components. Closest point and closest points with the plural, it's actually something quite handy. If you have a cloud of points, you can select one of them and then search for the points in its proximity. So cloud of points to search, point to search from, and then a number of closest points to find. So if there are, for example, 5 points that you want to find that are closest to this point you selected, then this would be a very good option. For example, we can test it here. If we take one point in Rhino here, for example this one, and put it there, maybe. Point to search from, this is the cloud of points to search. And I want to find only 2. These are the closest points to that one. So that might have gone quite fast, but I'm sure you can repeat that yourselves. So very, very handy things to use. You can find here. And you can also, if there are duplicate points, you can use this. Put all the points into the P input, and every double point is gone, because that could be the reason for double geometries, and we don't want to have double geometries. We can also project points onto surfaces, or any shapes with a project point, and pull points, sort points, and so forth. Here we have vectors that we construct. That we always want to use vectors when we move things. For example, let's move something. So I double click and type move. It's a component that actually comes later on in transform section, but whatever. Here we have, we take this point, for example, and we want to move that. Let's see, where is it? There it is. And it's gone up really high, huh? I'm gonna take out some stuff here so that we can see what's going on. So here is the point I constructed before, and now I moved it, right? But where and why? So the input T is a translation vector. So that's what the T stands for. And on default, it says 0, 0, 10, which actually, of course, moves it in X and Z direction because it's 0, 0, 10, right? But you can construct your own vectors. So this vector looks very much like the one we had before, the point we had before, So I can put in sliders wherever I want to here. Now it's all the same number, of course. And I use that instead. And then I can move it like this. So this is a moved component. This could have not only have been a point, but it can also be the curve that we had before. I can swap. So I don't have to. I can either, if I want to release a cable, I can go to disconnect, or I can simply just pull it off holding shift. But I can also, without holding any key on the keyboard, I can simply just put something in which will replace that previous cable. So here you see I apply the same move component to a vector, I applied the curve component to the move component instead of a point, and then I can move it around like this. So that is also very important to remember, that move components are the continuation of the geometry that you already had. So it could be a curve, it could be a point, it could be a surface, it doesn't really matter. It's simply another component being moved. So now it's still the curve inside, even though it says move here. A question that always comes up when I say that, you see it says move here, it's because it's about the display, the visual appearance here. So if you go to display and draw icons, you can have the icons there if you want to instead of text. You can also draw full names of all the inputs. So, but then of course they get longer and stuff. So that's, I usually appreciate when it's not like that. I want to have the names because that is also the main compact. I mean, it's a matter of taste. So this is the default setting. Some people like to show the icons instead. So that was vectors, and you can also see that you can also use only one a smaller component, only referring to the X direction, because here I used all of them. So if I dismantle all of these, disconnect them, I mean, this is actually the same thing, right? It's just that I'm using 0 and 0 for Y and Z, and here 0 and 0 for Y and Z is already it's taken for granted, because we only use the X direction. That's the only transformation we do. So you can test that by swapping, and you see it's actually happening exactly the same thing. So we can go over to curves, and we can see that we have analysis, division, primitive, spline, utilities. And this is the case for curves and surfaces, meshes as well. And I mean, it's structured more or less, these three are structured more or less the same. So curves have analysis first, division and primitive. So in the middle somewhere you actually construct curves, and to the left you analyze them. And it's the same for surfaces actually. Here you build them in the middle, and to the left you have analysis of them. Same for meshes. So on curves we can see that we can, for example, there are very many different ways of extracting data from curves. So I already do a curve, so I'm going to use control points now, and I can take the curve, put it in, and now we see the control points, very much like we do in Rhino. If we would, wait a minute, I'll use my moved one, and you can see the difference. The moved one, this is only existing in Grasshopper, by the way. So anything you try to grab in Grasshopper, it's not going to be grabbed, because everything exists only imaginary, so to say. It's not already existing in Rhino. But I come to that after we've done this. So here we see the control points, and they are actually exactly the same in Rhino as in Grasshopper, as you see here. So what if I want to extract these now and use these points? They don't exist, because that would take a lot of computer power, so it's only a simulation of what might come, so to say. You go to right click and you go to bake, and then you will transfer the geometry into Rhino. Like this. Sorry, that was something else. So now I have the curve actually being positioned here by doing bake, and the icon for that is an egg actually. So fried egg. You bake the sketch of what geometry you're working with. So when you work with surfaces, well, it's only a preview, right? So if they are complex, they're gonna look kind of strange in the preview, depending on the settings you have in the Grasshopper. Yes, so it's all imaginary geometry. You have to bake them in order to have use them in Rhinoceros. Yeah, so you can do even more stuff here. For example, you can go to point on curve. Now you can search a point on the curve based on its percentage, so 50%, or here is reparameterized into 0.5, which means the curve is divided into from 0 to 1, which is more or less from 0 to 100%, right? So if you have 0.5, you will find a middle point of it. But if you pull back to 0 is the start point, and 1 is the end point, and everything in between, of course. So analysis of curves. Here you can also find the length of a curve. You should try all of these out actually. If you hover, you see the exact line length in millimeters, because my Rhino is set in millimeters, and number of decimals is also referring to Rhino. So all the unit settings you have in Rhino will be translated also into Grasshopper, and it will use the same. So I can take those off maybe. You can also divide curves, very much like in Rhino. So you see also that the names are similar. So if you know Rhino, the commands you search for will likely be found. So I take that out and I hover here and see number of segments is already set to 10, and I enter there, and then you can see all of these are now divided into 10 segments, so 11 points then. And then you can actually split these into there's also in the same division, in the same section here, shader curve into segments. So this is like a mass split, you can say. Yeah? So you take the curve and you use the T output, which means parameter values at division points, and that needs the same here, parameters split at. So I can set it in, and then we have very many small curves. If I bake them, I can look at them as well. Bake, you see here, I made a mass splitting operation. If we go to primitives, we see that we can construct different things, like circle, for example. Take that out, position there. We hover, like always. I haven't really done it until yet, maybe, but you should always hover and read. If I go back to shader, I would have to have shader curve into segments. Output is shader remains, curve to trim, and then parameters to split at. So that's what you have to, if you want to use this shader component, you should have hovered all of them before. Very much as exactly like we're going to do now with the circle. Even though we know what it is, we hover. Create a circle defined by base plane and radius. Base plane, that means the position, right? So here is the base plane of the circle. Weld XY is already actually a preset value. So there it is already. And it's drawn already because the value here is 1. So I could take a slider and simply toggle between different radiuses like this, back and forth. And the same, of course, goes for the ellipse, which we also can find here. There's radius 1 and 2, of course. There's 2 radiuses in an ellipse. So if I have the same radius in both, it turns into a circle, but if I can stretch it like this, then it's different. So I urge you to go in and check all of these out. In another video I made about Rhino, I also showed the fit circle fit, which means you can use very many points to build a circle. And this is the same thing here. So if you hover it, you see fit a circle to a collection of points. What comes out? Resulting circle radius, like a number only, and the maximum distance between circle and points. So you get a lot of information here compared to what you do in Rhino, right? So we have a lot of points here. For example, these. If I use these and just put it into point input, it creates a circle accordingly. If I move my points, the circle will also be completely differently constructed, as you see when I move it here in Rhino. Yes. We can go over to line, for example. You can also hover that, create a line between 2 points, and then we have line start point and line end point. Now we can do a little test here. It would be nice if you did it too, because it does not have to mean that one point goes in here. You can make a multiple thing. So in this component I only have 1 point, but if I use all these and put that into B, I actually create 3 lines. So this is also the power of Grasshopper, that it can actually do this multiple things. So now it's attached a little bit to both. These points now control 3 lines and a circle. So it's a little test, you know. You gotta, in the beginning you have to play around a little bit, and then you will notice how it works and get a little bit more familiar with the whole thing, with the Grasshopper. Another thing we can look at here is if we go to splines, we can make an interpolation curve or a polyline, for example. So if we open a polyline, hover it, create a polyline connecting a number of points, we can select points in Rhino space, for example, or in here, and we just attach these. And one has to hold shift, of course, to add another cable. In this case, I made this 4 points connected. Actually, I had 3 in this already. So if I had 3 points in one of these components, I can simply attach it here, and it turns into a polyline instead of just one single line. As you know, in Rhino you can do either with a polyline, you can draw with a polyline, or with a control point curve. And the control point curve here is called interpolated curve. That means create an interpolated curve through a set of points, right? And the V input is the interpolation points. Here you can also swap between degrees, like rebuilding curve. So if I put these in like that, you see that's a completely different type of curve, of course. I'll delete a couple of things here so we can see properly. That's the polyline curve. And here, if I then toggle between different degrees, like 1 degree, and I delete my polyline curve, you see I can toggle between these. Of course, this should go to 3 degrees then, because the interpolation curves only understands 1 degree and 2 degrees. So here, for example, is an interpolated curve with 1 degree. It's actually a polyline. And then you go to degree 3, and it looks like this. Then it's a control point curve in Rhino, really. Yes, and all these splines here, they work very similarly to in how you draw in Rhino as well. You have, though, quite interesting things here. For example, the isocurve, which if you have a surface of some sort, you can take out its isocurve structure by using isocurve, for example, here. We can look at that afterwards. And I think you should go in here and try all of these components out, because it's hard for me now to do a really good example, but I show so many examples in my other videos, so don't worry. Utilities, we can explode a curve into smaller segments, like this. That's the component. You can hover and you can see what you can do with it. You can also join the curves. That I can apply, of course, to my shattered curves here. They were completely in disorder, and then I just add that to join as many curves as possible. And then you see a planar curve was made again, actually. So I joined the ones that I split before, right? Yes. Preserve direction of input curves, false. So you see here, depending on what direction they have, you can actually, in Grasshopper, go in and affect that as well in the same time as you're joining them. So you can do more here than in Rhino, actually. Here you can also find the very much used offset curve that you have in Rhino. So let's see, we can take this curve and put it into offset. You see there's a preset value of 1 here, which of course then moves it in some direction, but it's very powerful because it's simply, you can put a slider there instead, of course. Yes, and we were at curves. So the utilities, you can also project a curve onto a surface here, like in Rhino. By using this component, you simply add this curve to project and set the B-rep, the boundary representation, which could be, that is a term for a surface or a polysurface, right? So it's not, it's just to differ so that you don't think it's only a surface that is being used. There could be very many different types of geometries. So a boundary representation. Yes. You can rebuild the curve here as well. So let's try that one. I put it in and I rebuild the curve with a specific number of control points. Here, for example, I have 10. And you see what happened. It turned into something else. And then we have this degree situation again. So if I add that, degree 3, nothing's going to happen, but I can turn it into a polyline instead if it's a 1 degree curve, right? By rebuilding it. Sorry, 1. It understands 1 if I go to 0. So, yes. And here you can also fill in curves, which I showed at the beginning. We can swiftly jump to surfaces. So here you have freeform surfaces, and they are exactly working at some occasions at least, as in Rhino. So here you have a 4-point surface, for example, but with its own input. So if I have 4 points, I can simply take them in. So if I right click, set 1 point, right click, set 1 point, it's actually enough with 3, right? So then it will construct something already. And this is of course handy because the 4th point, now that looks a little bit weird, but that's great actually, because then I can show why this is so good. Because imagine you've done this in Rhino, and here you can simply just pull the point over and it turns into something much better looking. So now you have a sort of imaginary curve surface here, and you can sketch with the points until you're happy with how it looks like. So if I take, for example, these and just pull them up in front view, I will have a quite complex surface already. And this is not static. I can change it the whole time, so that's quite good. And here you see also the discrepancy of the preview, you know, of Rhino, of Grasshopper. So if I bake this, it's gonna not look like that at all. It's gonna look much nicer. And the surface quality is actually quite good, sometimes even better than in Rhino when you do it in Grasshopper. Rendered view, you see how it looks like that, but that's also, you probably cannot see it because of the video, but yeah, that's how it looked like. Yes. So if we go on, we can see that we also have boundary surfaces, which is planar surface in Rhino, situated here, surface from planar curves. So if I do any curve like that, for example, and I take that in, you can actually, you can also do this. So you import it into one of these curves, or you can import it directly into the input. Maybe it's a little bit more clean to do like this. So you select it like that, and input, and then you have a flat surface like that. So you should try all of these surfaces out here. Loft, we have, you know it from Rhino as well. You can then make many curves and put make them become a surface. For example, when I simply lift these up, whoops, that, and like this. Then I can insert these, set multiple curves in that case, right click, and then I create a loft which is constantly transformable. I can start changing my curves like this, and the surface is going to adapt, which is of course a very good way of sketching. Furthermore, you also have sweep. Just like in Rhino, you have pipes, but this is a much better pipe actually, because you can have multiple curves and they could be get piped immediately. So imagine you have, I can use all these curves instead, and I put that in. So no, sorry, yeah, well, we can take many curves at once. All the curves I've drawn right now actually. So you see, you can imagine that you can have numerous curves, and the pipe will simply adapt to all of them at once, which is of course very good. And you can also of course set the slider onto the radius and toggle between different solutions like that. So now we have quite much things here to see. So to explore the surface component here, network surface is also there, ruled surface is also there. It's a very good thing to do, so you understand how they work. If we go over to primitives, we can build boxes and cylinders and cones. And why are those actually under the surfaces? Aren't those solids, you might ask? But sphere is actually considered to be, is categorized as a surface, in fact, as well as a cylinder. Depends also on what, if you take out the cylinder here, if it's open or not, right? So if I bake this, you see that it's actually an open cylinder. Then it is a surface, technically. So in case you want to make this into solid, you have to cap the holes. And then I can jump already to the utilities here. So if you want to cap all the holes in this cylinder to make it a solid, you can go to this component called cap holes, hover it, cap all planar holes in a B-rep. And then you say B-rep again, like a boundary representation. Works for both polysurfaces and surfaces, right? So now I did that, and you see what happens. Now it's double geometry, that's why it's so red and green. And I bake it and take it out, and then it's actually a solid. So from primitive, you can jump to utilities to make a surface solid again. That's pretty nice. Here in utilities, you can also divide a surface into frames based on its ISO UV lines. You can offset the surface as well. Like I take this cylinder, for example, and offset it with a specific amount, distance. So you offset the surface, which is quite handy because then you use the normal of the surface, right? So that's the direction. If you go into negative, it goes into the other direction. So you can swap, you can simply edit the slider to make that happen. And on analysis, not to forget that, we can deconstruct a boundary representation, for example. This is an important one to remember because this is more or less like you explode a specific shape into its parts. Like if I have this, now I set one B-rep and I take this that I made before and put it in, it will divide everything here. Deconstruct a B-rep into its constituent parts. Insert a B-rep, and what you get is all the faces in a list, the edges, that means the lines that it's built from, and the vertices, so the points, the coordinates that controls its shape. Yeah, so surfaces, and we go to meshes here. You can have, meshes is something else than NURBS geometry, right? That's more based on triangular or quad faces. Usually used in different programs like 3D Studio Max or something like this. So you can construct this. So this is also communication with those programs. But what I want to show here is that you can, maybe the triangulation part is the most interesting. We can build Voronoi patterns, facet domes, Delaunay meshes, and Delaunay edges as well. And Voronoi, I have another video where I checked that out. But more or less, it's you can take a set of points and build a pattern from those points, calculating. If you consider every point to be a sphere, it will build cells accordingly, like this, for example. It builds a cell around that point and adapts to its neighbor, so to say. So if I go down like this, this is what happens in a Voronoi system. So now I'm dealing with the points here, and I can decrease the radius. And when I go up, it builds walls between the points in this manner. So I have quite much on the display right now, as you can see, only from showing, going through the menus. I watch on mesh here, and the same thing here as in surfaces. Really, you have utilities, you have your analysis of the geometry of the meshes you have. And I'm gonna work on this until transform here. I'm gonna show intersect and transform as well, and then we have gone through the menus briefly, and then I urge you to check out some other videos. So intersection, what is that? That is actually finding out coordinates between lines, for example. So it's mathematically, for example, if I have line and line here, and I draw a line like that in Rhino and line like that, you set one line, and I can use these now as reference, and set one line again. They will find the intersection. That's what they do. So that comes out of this. And you can imagine that you can do this on numerous curves, which is very handy indeed. That is the mathematical part of it. Contour you can also do, of course, if you remember it from Rhino. If you have a B-rep that you want to contour, and you have to then, of course, put in a distance, like a slider here. Now you can see what happens to it real quick. So here's my B-rep, but I will take that out. So here is the shape I made before, and it's been given contour lines that it can be denser or wider depending on the slider setting. So that's also on intersection. There you will find the contours, and you see that you can actually find the intersection between a curve and a plane, for example, or a curve and a line, a B-rep, that is a surface or a polysurface and the line, and so forth. If we go to physical, it's even more complex. So you have curve and curve with itself, or multiple curves. So that means we would have numerous curves here that I won't draw right now, but you can imagine that if you have a bunch of curves, you want to find the intersection points, very much like in the icon drawn here. Then you can also have something here like a surface and curve, so we can test that. it's a lot of information that's coming out. So the surface I have is, for example, the surface 4 point that I made, and then I can draw a line here in Rhino, for example, and draw it up like that. There. Now I know that it's going through, right? But we can still try to get that curve. And the fine part here is that every time I move this curve, a new intersection point through the surface is going to be generated. So this is how, more or less, how the intersection physical section here works. Then you can, of course, also split the whole surface, which you do with this component, which looks much more easy. So one surface goes in, and then you have a curve that is projected on the surface, and it will split it in 2 frames, very much like this. For example, I will, sorry. If I take pull curve, I take the surface and I pull a specific curve, namely the one I drew here. It gets pulled onto the curve, and I can use that as a split. And now I have 2 surfaces instead. I bake them, and you see I made a split here. Split this curve in half, this surface in 2 halves. And this is, of course, also very handy if you have a lot of curves that you want to split with, and you don't want to do it by hand. You can automate it with Grasshopper. So if we go to region, there's also a way of trimming. We can trim with regions. For example, if I have this and we have a line going inside it, we can trim that object. This curve would help from this component. So trim with regions, trim a curve. So curve to trim, I already selected that, and the region to trim with, set one curve, that's the circle, and then you see what's inside and what's outside of that circle. So both of these are actually now being made. So you see the split here works a little bit different than in Rhino. So this is the inside split trim, and that is the outside trim. I'll just swap the cables here, like that. So you can also do the same operation more or less with B-reps, so boundary representation, that is closed polysurfaces in this case, or several of them. Yes, or split. So it's interesting to look into all these components, and this was one example. So we also, in the last section here, we have shapes, region differences, region unions, region intersections, solid unions, and solid differences. The solid union is more or less like a Boolean union. So if I go to, I can show it quick. You can test it as well. So if you have a box, for example, like this, 2 boxes, and you take them in with the boundary B-rep and empty B-rep component here, and right click, set one B-rep, and take another one, set one B-rep. Now we can make a parametric solid union or solid difference, which is the same more or less as a Boolean union. So solid difference would look something like this. You hover, you say like perform a solid difference on 2 B-rep sets. So first B-rep set and the second one to subtract with. And then we move them together, and then it already happens. So if we then bake this, bake, you will see that something else has happened. I actually took that out of the whole system. Then again, to see this a little bit better, maybe move it so you understand what's going on. You can visualize it better than if we do like this. So this is the result of this difference, right? I cut with this from this one. And this is the moved solution result that I've done there. We can test another one here, for example. If I just do this and hold shift with both of them and move that instead, you see that that is the result of it. If I move them around, it makes a Boolean union perfectly and parametrically the whole time here, which is quite interesting indeed, isn't it? So we can, they're not intersecting anymore like that. We can also make a split period multiple with each other, of course, so you can test these out. Another thing we can do in the same manner is that we, very much like the path finder in Grasshopper, we have like maybe two circles here. And we do the same thing, but in 2D with curves, which is also very interesting for graphic design projects, which is also very good to do in Grasshopper. So now I have two curves there, and I will do a union between these. And what happened? I'll move it so you can see what's going on. Move a little bit more, sorry. So these are the things I'm doing right now. I have my I've moved the solution to the right, and when I move this, it actually creates a union between these two shapes. In the same manner, we can then extract as well using the other component here from a difference. So I take the first larger one, for example, into the A input, and into the B input I take the other one, and then I replace this so you can see the solution. So every time I move something, it gets cut out from there. If I go inside, of course, it's actually doing this as well. So, and this is a closed curve now, so you can make a boundary surface from it. As a matter of fact, like this. So this is a perfect surface now, flat one actually. So these are very much, I recommend testing these out. Here, for example, we have the what comes in between as well instead. So this is the space between the shapes. There has to be closed shapes though to work. Yeah, so if we look at this move component, we can find it under the transform section right here. So here we have a lot of different things. So on the transform section is where you can find, for example, you can shear things. You can that means you can simply tilt shapes, or shear is actually a better word. You can orient objects. You can project objects onto a plane. You can map things onto other geometries. You can array curves and points in polar array, for example, not only a rectangular array like a grid, but in a circular movement. You can also mirror things, you can move things, that is this component, right? It's actually this one. You can orient things, that means moving them from one plane to another plane, which can be made then on numerous planes, for example. And here's also the rotation components. So practically the whole transform section is to reposition or arrange objects or even stretch things and morph them, which you see here on the next section, which means that you can have, for example, a rectangle or maybe a box, and then you can twist this one so that it fits to the surface. You can use the geometry of a surface, like a doubly curved surface, put a box onto it, like a solid shape that gets bent and deformed according to a target surface. And then you also have utilities here, which means that for example, you inverse the transformation that I just described. You split the compound transformation into fragments. So what we can do first is simply to scale, like we did before. We have our solid difference, solid unions, maybe we can use, by the way. So I'll move that instead, and we can work with this one, check it out. So, by the way, as you saw this before, a curve was attached to the move component, and then there's a curve which can, from that curve, a boundary surface can be made. If I attach something else, it's not a curve anymore, is it? It's now it's a closed B-rep, so that no boundary can be generated. And it turns red. So that means that's a sign for something is wrong. So we have this moved component here. This is my the original shape, and I can scale this very much like in Rhino. It's just we have to decide on a center point here. So if we hover, see scale an object from uniformly in all directions, 3D scale. This is the object we want to scale, and here is the center of scaling, which we don't really have, or do we? There it is. It's in 0, 0, 0. So in all these cases, one has to go in and actually analyze the structure. For example, like with a volume on surface analysis. If we apply a volume to the original object, this object, we get a center point, and we can scale from that. So there you see it's a scaled version of it. You can also use area for this, because area and volume always generates a center point. So to this you can of course add a slider. You saw now that I took it from the left lower corner, and this is a guess. The program is guessing which one you, based on what you've done so far, it's guessing what components you want to have, which is quite handy. So if I hide these, and then I can scale up and down based on the center point that I just set. Right. There are more scalings. It's also scale non-uniformly. Sorry, wrong. Here on transform, and we can go to scale non-uniform, which means that we are scaling only in one direction. The same thing you can do in Rhino as well. So if we can delete that and just scale in X direction, for example, and hide this, you see that it gets only stretch in one direction, or maybe you want to do it in Y direction, like this, or maybe you want to do only a 2D scale. Then you attach the slider to X and Y only, which means it actually doesn't scale in Z direction. Yes, and here we have very many of these different orient direction, for example. You use then a reference point and a reference direction, and a target point and a target direction, which means that you can reposition things accordingly. So then you just have to set the origin point and a vector, and that should be mimicking the target. If we go on, we have box array, we have curve array, we have rectangular and polar array. So we create a rectangular array of the geometry. Okay, maybe we should apply it to this now actually. So we have our scaled object, let's say this one, and we need the center. Let's see. No. And we have, I meant this, not the center. fitta. So you can use this, for example, we can use our scaled object. We can do a rectangular array and attach this. And you see that it multiplies around it. We can also use a polar array like this. And now the center point is actually here, so that's why this gets moved. But you can put another plane here just to show how it works, like this. And objects gets rotated around like this. And you can then actually set a slider here in the middle, maybe from 1 to 10, with an integer, of course, because it only works with integers. 0 will make it not working, and then you can put it into n here and simply multiply them around the center point like this. These are the things you can do here. Maybe one can apply it to something else in exactly this shape, but who knows what you can need it for. Yes, so that's the polar array transformations. Then we have the Euclidean rotations. For example, mirror. If I put that in and use it also on my shape here, I need to have a center point. On default, it is on world YZ here, which is of course a bit strange because then my object lands over there. So if I would put the mirror somewhere else, for example here, now it turns into a XZ, you know. So now it's an XY. So the mirror is now downwards according to this plane that I just set. We can also rotate the object based on radians. So here we have a rotation device. I'll take out my mirror, and we have to set another plane as well here, so around here. And then radians is actually something that we work with the whole time here. Radians is based on pi, so 2 pi, that is 6,28. That means 2 complete revolution, 360 degrees. So in this case, it reacts on very low numbers here. So you see already that from 0 to 1 it makes quite much. And that is because the default value you see here also is now a half a pi, which is 90 degrees then, going from there to there. It makes sense. But if you want to work with degrees, you can right click and go to degrees and then have a slider from 0 to 360 to put in there. And all these inputs I'm gonna deal with in another video as well, because they are quite crucial. So you go around like that. If we go further, we to the next one, morph. We can map patterns onto a doubly curved surface, and I want to show one of them called map the surface real quick. So I will now actually delete everything I drew here and make something new. So we end this video with actually making an interesting grid and map it onto a surface just as a little test. So I'll delete this, and I can take out that as well, and all my things here, and we start a little bit from scratch and make a grid together and map it using morph. So we're gonna jump from vector, grid to morph. Okay. So if we go back to vector and take a grid, we can look at that a little bit more closely. Let's take a square grid here, for example. Take that out. And now we remember that we are hovering things. I can go to top view and look at it. We want to hover on everything we do. So 2D grid with square cells renders or generates grid cell outlines and points at grid corners. So we here have a base plane for grid, which is always in 0, 0, 0 if we don't change it. We also have a size of grid cell is 1, and we have number of grid cells in base plane x direction 5 and 5. So what we can do now is to take out some sliders that you find here, right? I took it from the lower left now because it suggested it. So one of them can be the size, maybe, like that. And another one has to actually start with 1, because you cannot have less than one cell in each row, right? Otherwise the component would turn red. So I'll take, for example, from 1 to 10, or you can put whatever you want to and go to integers, because it's going to be integers anyway. And then you can just simply change these. And then I did a copy paste on that last slider there. Yeah, what do we get out from this really? We can do a lot of things. We can scale this down, all of these individually, or we can use the point system in order to place something there. For example, if we want to scale these down a little bit, we double click and search for scale. And we remember where that was. There was on transform right here. In this case, we can do a 3D scale because they're 2D objects. It's going to be 2D anyway, so to say. So if we scale all these, what's going to happen? They are just going to be much smaller down here. And now there are 3. It looks like 3 different grids, right? But the thing is that every time you use a square grid, they're gonna a plane is default set into it, so that is visualized in the same time as I click here. That could be a little bit irritating. So either one simply shuts that out. Now we only see the transform grid. The other plane that you saw here, this one, if I show now in Rhino space here, is inside of this input already on default, right? We can assign another plane and then it would be gone, but it's very good actually that it's visualized, I think, because then you see exactly where it's positioned if you have a complex system. So I will turn that off, and then I have scaled the whole thing, right? So if I put in a slider here into the F component, it goes up and down like this, and this is not really what we wanted. That's why we need to extract the center point of the cells, and that we do with area, which I showed earlier as well. So on surface analysis, we have area component and volume component. So area would be good for this because there are closed curves, and I put in take from the C output into the G input. And all of these center points are generated. That I can use as scaling actually. Now it becomes individual points and individual scaling operations going up and down like this. Now we already have a pattern actually. I can hide these, you right click and go to preview and they're out. There's also a big difference between right clicking and going to enabled, because then you turn off the function of the component. So that's 2 different things. Now I went to enable again, and the preview is off. So this is more or less the result of the little pattern study that we just made. What can we do more? Well, we can actually visualize the points here as well. They are not visible in the grids. So you have to extract them with using the point object here, and then you see all the point corners as well, if you need them at all. The thing is, what I want to do now is to, I can hide these again. I just want to show where they are and how to visualize them. Either I can use this as my pattern now, or I can draw something myself. So for example, if I go into Rhino view here, and let's make a star, for example, then I just click on star. Where is it positioned? 0. Number of sides, maybe 5. And then I try to make a star that is more or less the same size. This, and I pull in, and then we have star. You see second star radius. Now I can use this and transfer it to all of the center points that we generated. Then I don't really need this anymore. I just want to show 2 different patterns at once. So we can call in this star with the curve, right click, set one curve, right? And what do I do now? Well, all of these points and all these center points here, if we look at these, for example, these are placeholders. These are also vectors because they refer as a vector. If I take a move component now, it would analyze the center point of the star. That's why I made it in the center, and the vector to each and every position in the grid. So let's go to transform and open move, and we hover it. Translate or move an object along a vector. So the geometry that we want to move, we already have that. That's our star, right? And what's up with a vector now, really? Well, the star already has a center point. I drew it in 0, 0, 0. The vector that we can apply to it, we can do that in many different ways, but we already have the end position of the vector. So it's from here to there, to there, to there, to all the points, which means we can simply put all of these points into the T and we'll understand what we mean. So let's try that, like that. Then we have stars all over the place now. So now it's like overlapping patterns, of course, but if we select these and click outside and take preview off, our pattern is there. This can also be mapped onto a surface, and that's what I want to do here with the transform and morph. So if I double click and I make some interesting shapes here between, like a curve like that and another curve, and the second curve I want to erase, of course, in the set direction. Just to give you an idea, after this long intro you can have an idea of something you can do and try out. And I have more videos where I use mapping like this as well. So what I need to do now is to take both of these curves in. So I go to the first parameters, take out one curve, copy it, right click and set one curve, and right click and set one curve again, the other one, of course. And then I can build a surface between these, like I showed before, like on surface here. I can choose, in this case, either loft or maybe ruled surface. Loft I showed you already, so I go for ruled surface. It's quite good actually because it has two inputs, which means the order of curves is never really a problem. So I'll put this curve in and this curve in, and then I have a target surface. So what I want to do is to map all of this onto this surface, and then as we pull the curve, they will adapt. So in order to do this, we need to look at the map to surface component on transform. So now I explain a little bit exactly how this works. That's one example. Then it's very many other components that you have to look into as well. But it's more or less, if we open it, map to surface, more or less like a reference surface and a target surface that are involved. So if we hover this component, we see map a curve onto a surface via control points. That's what it does. So the curve to map is definitely the moved, all of these moved stars that we made, like that. And then we hover again here, base surface for initial coordinate space. That means a source surface, like a initial surface that is to be mimicked. And mimicked onto what? Onto the next input, the surface for target coordinate space. And that we already made, right? That is the target, so we can put that in already. But nothing happens because we do not have a reference surface. And how do you make that? Well, we can actually draw a surface in Rhino if we want to. So if I, for example, go in here and I make a plane, rectangular plane, corner to corner, and I make, for example, like this, just an example right now, and I communicate this surface into Grasshopper, we can use that as a source surface. So I go into parameters and surface, right click, set one surface. Now it's inside. I could have taken it directly from here as well, but it's a little bit more clean if you do it with a individual component like this. And then I put that in, and the system is working already. Yes, so that was a small overview of Grasshopper, a small introduction of Grasshopper. And I want to encourage you to go in and look at all the sections and try things out. And also play around, of course, with this last setting, because every time you move something around, they will be mimicking this movement accordingly, analyzing this space. And if you transform this source surface like this, if you scale it, for example, the mimic will happen on the target surface as well. Of course, you see that they are stretched a little bit, and then one wonders if that could be dealt with, and yes, it can. And that is to be found in my other videos. I hope you enjoyed this one, and I hope you also look at the other videos that I made. Thank you.